Hello and welcome back to Calculus, the series where we explore derivatives. First, I'd like to thank all the nice people that support this channel by liking and subscribing. Now, please recall from the last video, we explored the concept of derivatives through the first principles. We were able to calculate the gradient at a specific point and compute a general expression for all gradients on the graph. However, computing derivatives that way is very time-consuming and difficult for more complex functions. Thus, today, we will introduce differentiation rules in order to make our lives easier. Now, firstly, please recall that we can express the derivatives with three different notations. Now, out of all of the differentiation rules, the most general and commonly used is the power rule. Let's say we have a function f of x equals to x to the power of n, and n in this case would simply be a real number. Well then, the derivative of this function would simply be n times x to the power of n minus 1. As you can see, what happened here was we took the original power n and we put it in front as a coefficient. And then we subtracted the original power by 1. So for a brief and simple example, if we have a function y equals to x to the power of 2, then the derivative would simply be 2 times x to the power of 2 minus 1, which in this case is 1. Now, since the power of 1 doesn't change anything, we can simply not write it. Now, this leads to two very common questions. What happens when we just have an x or perhaps a number times x? Well, in the first case, the y derivative would simply be 1. This is because x originally has the power 1, and once we do its derivative, that means the 1 moves into the front, and then power minus 1, which in this case is 1 times x to the power of 0. And anything to the power of 0 is just 1. So we have 1 times 1, which is just 1. Similarly, for 2x, the derivative here would just be 2. So anytime you are computing a derivative of x to the first power, just know its derivative is just going to be the coefficient attached to it. Now, another case that may arise is what would be the derivative of a simple number, for example, 3 or 2. Well, since constants do not have any x value attached to them, their derivatives would just be 0. Of course, functions are almost never that simple. Usually we have the addition and subtraction of several components. As an example, I'm going to use f of x equals to 4x to the power of 3 plus 5x squared minus 6x plus 7. Luckily for us, in differentiation, adding and subtracting components does not complicate our calculation. We can just compute all of these derivatives separately and then add them or subtract them. The derivative of 4x to the power of 3 would just be 12x squared. Derivative of 5x squared is 10x. Derivative of 6x is simply 6, because x is raised to the power of 1, so x vanishes. And lastly, we have the constant 7, whose derivative is just 0. Now all we need to do is put the respective signs back in their positions. And here you go, this would be our derivative. This looks easy enough, so let's take a look at a more difficult example. Here we are given the function y equals to 2 over the cubic root of x minus 3 over the fifth root of x. From first glance, this looks extremely complicated. However, the roots and the fractions can be rewritten. The cubic root of x means x is raised to the power of 1 over 3. And of course, the fifth root of x means x is raised to the power of 1 over 5. And now finally, in order to get rid of the fractions, we can use the negative exponents rule. So this would simply be 2 times x to the power of negative 1 over 3rd minus 3 times x to the power of negative 1 over 5. So now we can actually apply the power rule. So 2x to the power of negative 1 over 3rd, the power goes in front, and we get negative 2 over 3 times x to the power of negative 1/3 minus 1. Following that, we have minus 3 over 5, two negative signs, times x to the power of negative 1 over 5 minus 1. To simplify all of this, we would get negative 2 over 3 x to the power of negative 4 over 3 plus 3 over 5 x to the power of negative 6 over 5. And this here would be our derivative. Here you can see that we have to rewrite the roots into exponents. It is also why I said it was crucial in the introductory video that you know how to rewrite rational exponents. Now, today let's end the video with a little question. How would you compute the derivative of the following function? 2 minus 11x to the power of 10. If you said this is easy, it's just 10 times 2 minus 11x to the power of 9, you would be almost correct, but not completely. Computing this derivative here requires something called the chain rule. This is probably one of the most crucial differentiation rules to ever exist, and we will cover this in the next video. So I hope to see you there, and have a nice day. Bye.